Okay, so I'd like to thank the Quicycle crew, particularly John and Arnie, for arranging this talk. Since we all come from different backgrounds, we all have different ways of visualizing and processing the laws of physics. However, we've all gone through similar learning experiences in the interpretation of images through our visual system. So today I want to use our shared experience of image interpretation to draw an analogy between how we see quantum mechanics and how this mirrors features of visual processing. I want to argue specifically by using images, avoiding equations. So we're going to think about perspective. And, here we see some bicycles in imminent danger of falling, or perhaps not. If we look carefully at the images, we may find out that our initial assumption of perspective is not quite correct. So if we look at this image, well, this is a very well-known image. And the thing is, our perspective determines how we interpret what we can see. And, this interpretive feature of our built-in image processing is learned, but seems fairly automatic. But we can adjust it to changing input. And in this talk, I shall argue for a number of perspective changes, figuratively speaking, in cases where a conventional perspective is in question. So, for example, in the horse and train image, we don't see the horse as being bigger than the train. We automatically adjust for the perspective which we associate with where we are. And the thing is that perspective does determine how we interpret what we can see. And it even does that when what we see is not quite right. If we look at this wonderful image, we can see that our visual system, our interpretation is a bit fooled, and we can all imagine days when we are really the monks that are on the outside of the staircase. So what I want to do is I'm going to show another slide, and I want you to just, when you see the slide, note your visual processing of it. That is, in a sense, try and observe yourself observing the slide. So here comes the next slide. So this is an image that many people interpret as a sketch of a staircase. And if you see a staircase here, ask yourself if you are viewing the stairs from above or from below. Most people's initial impression is that you are looking at the stairs from above. However, there's another way of seeing this. So if you see those as a stairs that you're looking at from above, try and push the area A into the background behind B, or alternatively look at the area B and try to bring it into the foreground. And when you do that, you will see that you can actually flip between two different interpretations of the same image. And it's quite, well, when you do it, you'll see that your interpretation of it just shifts, and it's hard to see them both at the same time. You tend to flip between one and the other. And so we might ask, well, what's happening here? Well, the image itself is two-dimensional. It's just a bunch of lines on the plane, and it lacks the detail necessary to infer a unique projective transformation from 3D to 2D. So the visual processing pushes our interpretation into the most familiar perspective, which is usually for most people, it's the above stairs, where we're actually looking down on stairs from above. So the below stairs perspective is nearby in a sense, given the restricted information, so that we can see the interpretation as well if we try. So we can, we can once we get used to this image, we can flip between the two interpretations. My claim is that a similar bistable picture exists for the relationship between special relativity and quantum mechanics. So here is my suggestion for what is the usual, in a sense, the above stairs perspective. So this, in a sense, goes along with history and pedagogy. And, you know, typically we start with Newtonian mechanics, and then we sort of, with much waving of hands and matter, we look at Schrödinger's equation. And then after some wrestling with relativity theory, we have a look at the Dirac equation. And of course, the exit from quantum mechanics is to probability theory. So in a sense, that's the historical perspective of how quantum mechanics works. We tend to go from Newton to Schrödinger, and we tend to stay there unless we have to talk about stuff that is relativistic. But there is another way of looking at this. And the other way of looking at this is to say, well, look, if we wanted to look at the theory proper, we all know that we live in a relativistic world. So really, we should start with special relativity. And then if we're sort of going from special relativity, then we should go from relativity to Dirac. And, you know, we know that if we look at a low speed approximation for Dirac, we should find the Schrödinger equation. And if we then look at the correspondence principle, we should get back to Newton. And so there are these two different ways of looking at quantum mechanics and its relation to special relativity. My experience is just about everyone I talk to really lives in the first interpretation. It's the above stairs one. So one question is, well, why should the different perspectives be important? Why worry about them? Well, in this case, it is a bit important. So like the Schrödinger stairs image, both the Dirac and the Schrödinger equation lack the information we need to interpret the algorithm. Right? So just going back quickly. So here I'm calling special relativity and Newton and probability and theory as being theories, whereas I'm in a sense relegating quantum mechanics to algorithms. And there's a bit of a justification for that, and we'll come to that. So yeah, so why is this important? It's important because when it comes to quantum mechanics, we have this peculiar thing that we have things tend to propagate as waves, whereas they're observed as particles. And this is really unexplained. I mean, we have the name wave-particle duality, but it doesn't really explain much. It's sort of, we're just saying this happens without an explanation as to why. So we shall actually see that the reason for this and the actual origin of the feature becomes visible only when we make a direct link to special relativity. So in a sense, the below stairs approach is quite important. So let's just question this theory status. If you said to most physicists that, well, you're thinking of quantum mechanics as being an algorithm, and comparing that to theories of Newton and probability theory, they would probably be a little bit annoyed at this and come back and criticize the whole idea of theory versus algorithm. So let's put ourselves in the position of an annoyed physicist and declare that special relativity and probability probably aren't as exalted as is made out by the diagram. So here's a question that might be asked: if probability theory is so great, why does it appear to fail in the Young double slit experiment? Right, that's an example possibly of the failure of probability. And also, if special relativity is so great, how come it completely overlooks quantum mechanics? So these are questions that you can legitimately ask if you're going to try and say that quantum mechanics is in a sense, an algorithm as opposed to a theory which provides an explanation. So let's have a look at these two questions. So first of all, let's have a look at probability. Well, we just have these three axioms that we've looked at before. So we're trying to measure events. So we need a probability measure that's real and it's non-negative. And we set up an event space and we normalize the event space and say, well, the probability of the sample space is 1. And then the thing that really makes the probability theory work is the additivity. And that is, if you have a bunch of different events, then provided that they're disjoint, the probability of the union of the events is the sum of the probabilities. So that's our additivity postulate. But notice sort of the generalization of that is if we're looking at the probability of the union of two events in general, we can say, well, the probability of A union B is the probability of A plus probability of B, and we don't get the subtraction. Well, the subtraction is irrelevant if A and B are disjoint. So we get back to this feature where we can just add the probabilities of events. So if we now look at the double slit experiment and look at this suggested failure or possible failure of the probability model, we can see, okay, well, supposing we have an electron source, we have a double slit, and we look at the result of the experiment, and we see one of two curves. Let's see whether okay, so we see one of two curves. Now, if these were classical particles, we would see the probabilistic superposition principle. That is, we'd see these curves here added together. So if A represents the event passage of a particle through the upper slit, and B represents passage through the lower slit, then classically the intersection of A and B is empty, and we should see the probability of A union B is the sum of the probabilities. So that's classically what we would expect. Now, of course, in the actual double slit experiment with indifferent fringes, unless the probability theory itself fails, passage through the slits A and B cannot be disjoint events. Right? It has to be one thing or the other. Either they're disjoint events and given the result, probability theory fails, or the passage through A and B are not disjoint events. And that's, of course, the out that one takes eventually in quantum mechanics. So that's the double slit experiment. And the thing to notice is that the whole idea of particles going through both slits makes absolutely no sense in a Newtonian spacetime. So if electrons really are like classical particles, one just there's no sense to the experiment at all. So let's have a look at special relativity. We're going to rearrange the Einstein postulates for convenience. We're going to a postulate that is actually part of special relativity, but is usually taken in a sense as an assumption. And that is that associated with any particle is a world line. And that assumption I'm going to call the one. The many is that all inertial frames are equivalent. So this is a very, very strong assumption, but of course it's an assumption that's made in Newtonian mechanics as well. And the thing that really turns everything on its head is, of course, that the speed of light is constant in all frames. So if we put all those three together, we can end up with Minkowski space, and putting in dynamics, we get special relativity. So the first two postulates are consistent with Newtonian mechanics, and it is the last one in combination with the first two that forces a replacement of space-time with space-time. And the thing is, for particles with only one bit of information to distinguish the position on a world line from the background, 1 and 2 do not explicitly conflict. We tend to believe both of them. And so to the extent that special relativity is consistent, the ontology underlying 1 and 2 doesn't really need to concern us. However, of course, special relativity misses quantum mechanics. As such, the postulates themselves must be inconsistent or incomplete in some way. So what we're going to do now is we're going to actually look at some images of just space-time diagrams of free particles in 2 dimensions. And we're just going to tinker with them a little bit to see whether we can see what happens if we put a bit of extra information on the world lines. So here's an example of a particle that's stationary in the lab frame, and it exists at least until its proper time of 10 and then seems to disappear. So that's what's listed here as a 1-bit clock at rest. So the 1 bit just determines the presence or absence of the particle. So in a sense, you can think of it being a delta function that's just sitting at the origin and persisting in time. Here, of course, we use the usual convention that C is equal to 1. So let's just have a look at a bunch of these. So here's basically a space-time diagram of a single 1-bit clock, but there are images from different inertial frames that are synchronized at the origin. So here, the thing to notice is simply just the time dilation, the stretching that you get because of the Lorentz transformation. And also notice that you know, we're really looking at the future light cone from the origin, but we can see we're in a sense traversing it with these one-dimensional homogeneous subspaces. So we can look at a whole lot more, and in the end, of course, we will. There's uncountably many of these one-dimensional subspaces that we can fill in the light cone, and we will have these subspaces distributed throughout the cone, and it's the equivalence of inertial frames that specifies, you know, how this ensemble plays out over this future light cone. So what we want to do at this point is we want to just give the world line one extra bit of information. So we know that the 3 postulates above encoded mathematically give us Lorentz transformations in space-time, and quantum mechanics is overlooked by special relativity. But here's the claim. So it becomes visible with 1 more bit of information. So we can show this by looking at some familiar images from a slightly different perspective. And so we'll just walk through a sequence of images that shows the extra information uncovered by an extra bit. And it turns out that the reconciliation of the extra information with Einstein's postulates leads to a context and ontology for wave functions within special relativity. So we're going to now look at the idea of 2-bit clocks. So think about a world line where we mark periodically events. Well, those events define a causal area between successive events. And we're going to, in a sense, color the interval between those events by, we're only going to use 2 colors. We should use 4, but it's easy to see what's going on if we just use 2. So think of these events, and the world line between each event is colored by either red or blue, and it's done periodically. So if we do that, we can say, well, okay, here's the original world line that in this case disappears at t is equal to 11, and you may or may not be able to see it easily in your resolution, but now the world line is colored periodically red and blue. And let's have a look at a bunch of them. Well, when we do that, we see that, oh, we begin to see this pattern. And the pattern is really making the idea of time dilation local. So we can locally see the stretching when we do a Lorentz transformation. So here's the whole lot of them done in such a way that we can see all of space-time is, in a sense, colored by what is really a single one-dimensional subspace. So think of that initial world line that's just got the two colors on it. And all we're doing is we're repeating images of that under the Lorentz transformation. So notice that each one-dimensional subspace has a frequency associated with it, and the frequency is different in the different subspaces, and it's determined by velocity. So let's now think about the image at a fixed t. So here, if we think of drawing a horizontal line at t is equal to 10, and looking at how it intersects all of these one-dimensional subspaces. So what happens is, imagine coloring the line according to the color of the intersection of the 1D subspaces with t is equal to 10. So let's get rid of a bunch of information on this, just so we can see more clearly what's happening. So here we've just thrown away a bunch of the ensemble, and we're still looking at the horizontal line, and we can see that, oh yes, there's this periodic pattern that appears on the line. And so let's throw away the rest of them. And so here we see that we have this at fixed, that t is equal to 10. We have the intersections have colored this line in such a way that there's a broad blue area in the middle, and then a periodic red and blue to either side. And I'm going to call that thing a history map. The reason I call it a history map is because it is a map of the history of the particle back to the origin, in the sense that if you look near the x equals 0, you're looking at the recent history of the particle. And as you head out towards the light cone, you're going farther and farther back in the history of the particle, until when you actually hit the light cone, you're hitting the history of the particle at t equals 0. So this impression along the fixed t position is a map of the history of the particle. So let's make it a little bit more obvious what it looks like. Here's what it looks like. Maybe perhaps too obvious in this case. So here, all we've done is replace the colors by blue is +1 and red is -1. And you look at this thing, and you might perhaps look at it, and it might ring a few bells, right? It looks a little bit like a square wave wrapped on a cylinder, or it might make you think of Bessel functions, or it's possible it might make you think of the Feynman propagator. So let's just investigate that. So here is that curve, just on a slightly different scale. So the blue thing is just the history map. The brown area, the continuous curve, is the real part of the non-relativistic Feynman propagator. And just note that the sign of the binary clock and the propagator are completely the same. And the discrete phase of the binary clock is 2-bit special relativity alone. Right? There's no quantum mechanics in this whatsoever. This is simply a special relativity where you've put an alternating color on the world line, and then looked at the images of the of this world line through different Lorentz boosts. So the thing is, what registers those patterns? Well, it's one number. It's m in terms of h bar and c gives you the registration of that pattern. So The one thing to really note here is that pattern and the suspicious correlation between the 2-bit clock and the Feynman propagator. That is all Lorentz transformation, right? If you're in Newtonian space-time, space and time are independent. You don't have that hyperbolic pattern, so you have none of this, right? And what it really means is Schrodinger's equation, or what it's really doing is it's placing an overlay on the Galilean transformation. So its route to quantum mechanics is quick, but not terribly well motivated. Okay, so just to summarize again, if we're looking at 1-bit images, we think of, so on the left-hand side at the top, think of a single world line that dies off here at t is equal to 10. So that's the one. There are images of that under the Lorentz boosts, and you reproduce this structure. But because you're in the continuum, you don't see the local. You don't see the local time dilation. Whereas if we give the particle a 2-bit clock, well, yeah, we do see the evidence of time dilation locally, and we get this history map. Okay, so what about this recognition of 2-bit relativity? So the space-time patterns created by an extra bit of information, they go unnoticed in classical special relativity because there's nothing there to recognize, right? So the one world line and the many, the ensemble of inertial frames, they coexist peacefully. However, the extra bit of information brings in aspects of signal processing absent in conventional special relativity. And the conflict between the one and the many can be illustrated by a double slit experiment for 2-bit clocks. To consider this, we have to allow 2-bit clocks to change inertial frames. So we've got to have some regime for doing that. So if two piecewise inertial frames exist between source and observation point, we're going to have to ask the question, well, does the many postulate, the idea of ensembles, dominate or not? Do we stick with the idea of the continuous world line? So let's have a look at a piecewise inertial frame. So here's probably a familiar looking idea. So we think of a stationary clock, which is this series of blue and red rectangles sitting along the t-axis. And then we look at that thing and say, well, okay, in a sense, this is a clock that goes through 5.5 cycles. But then we're also considering this hinged frame clock, where we go out at one velocity and switch at a point where the rectangles converge on a single event. And we look over that and say, oh, well, look, so in this hinged frame, the clock only executes 4 cycles. So here, age and what one might call parity, where they meet at the endpoint, they disagree. And the age disparity, of course, we know all about, right? That's simply an example of the twin paradox. But that the parity disagreement is simply not considered in special relativity. Right? It isn't directly considered. The twin paradox is there, we know about it, but we don't take it down to the idea of actually bits of information. So what about the idea of hinge frame equivalence? Do we have an analog of that when we allow a piecewise linear path? Well, here's a sketch of a stationary clock and one in a hinged frame. The initial and final parity agree, and both clocks are periodic, and they differ by 1 complete cycle. And the thing to notice about this is we can look at that and say, well, okay, with a full cycle missing, the hinge frame clock is indistinguishable from the original viewed from a hinge frame at both the source and the sink. In a sense, it's simply an image of the same clock. So we can look at this thing and say, okay, so look at these two, this pair of paths. There are two possible ontologies here. One, there are two separate but synchronized clocks. This is just simply the twin paradox, the usual case. Or we can say, well, there is one clock but two images. So as in the equivalence of inertial frames postulate. So this is closer to that postulate. So the thing about the latter interpretation, if the latter is the case, the extent to which the second postulate builds spacetime, it now has to account for the whole hyperbolic pattern, not just at the ends where the particle disappears, but the entire pattern. So here's the idea. So let's just extend inertial equivalence. So the second relativity postulate demands the equivalence of all inertial frames. So a minimal extension of equivalency will be to demand preservation of parity between hinged paths at source and sink. This preserves the idea that the ensemble of inertial frames is really an ensemble of images of the rest frame. So the extension preserves the equivalence of the local history at both the source and sink, up to 2 bits of information. And this is consistent with the picture that there is really only one rest frame signal, the other being images of the original signal over an ensemble of piecewise inertial frames. So what about inequivalence? Well, so equivalence between paths means that they differ by full period deletions. Inequivalence means that they differ by partial period deletions. Physically, inequivalence means the two paths are simply not Lorentz transformations of images of the same clock. And if we choose a binary characteristic function that's plus or minus 1, opposite parity at the ends of the path eliminate an inequivalent pair from contributing to the propagator. So this is thinking about the images of a single path as being a propagator. So what does this do? Well, it implements an exclusive OR for paths in the following sense. So if we look at the left, if we have two blue paths coming in a sense, that's a yes. If two red paths come in, it's a yes. If a red and a blue path come in, that's a no, because they're not images of each other. So you can just set up a little table and see that, oh yes, well, if you get two ones, you get one. If you get two minus ones, you get a minus one, and that's fine. But you also notice that if you square that, the square of the function gives you back a characteristic function that's either 0 or 1. And so that, indeed, is a function you can use for counting and hence for probability. So let's revisit the old Young double slit experiment. And so what we're going to do is say, well, let's just add the indicator function for inertial equivalence. So the question is that what we should do, or should we add it square? Well, we know what happens if we add it square. We get classical particles. So if pairs of paths through the double slit are hinged inequivalent, the contribution of the paths cancel. So if in adding clock signals filters out inequivalent paths and invalidates the classical assumption that the world lines going through A or B are disjoint events. So let's have a look. We can do this experiment simply numerically and see what happens. Okay, so here's the 2-bit digital clock versus the path integral for the double slit. So this is the square of the real part of the propagator. That's the curve in brown. The square of just this 2-bit clock from special relativity. We look at that, and this is the central 3 interference fringes from a double slit. Okay, and you look at that, and this both show the midfield interference effects. The gaps in the bit state graph correspond to cancellation of inequivalent paths. So there's a bigger look at it, and you can see it's in the end the 2-bit relativistic clock knows all about the Feynman propagator and how it relates to the double slit experiment. So so the Brown region is the square of the real part of the wave function from the 2 point sources, just using Feynman's propagator. And it shows the central 3 fringes of the interference pattern. The blue area indicates the same calculation, but for the 2-bit relativistic clock. The fringe here corresponds to the yes-no answer to the question, are the 2 paths 2-bit inertial equivalents of each other or not? So the Feynman calculation is just a smooth version of the relativistic one. And the difference is that we know what the relativistic calculation is actually doing. We know that. It's just filtering for the Lorentz equivalent images. It just asks the question at a point on the screen that asks, well, the paths that end up here, are they all images of a single thought? So the question arises, we can't really avoid it. Do we add signals as opposed to probabilities? Well, classically, of course, we would expect to add probabilities at the detector screen. And this is because we expect passage through either slit to be disjoint events. So the probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. But the intersection is empty, so it just is a sum. Right? That's the classical idea. But here's what we've seen. If we give the particle an extra bit, making it a discrete clock, it forces us to reconcile the one and the many in special relativity. The natural extension requires both paths to be images of a single rest frame path, agreeing at both source and sink. This means that here, A intersection B is not empty, and it's a consequence of Einstein's second postulate. Basically, that space-time tells particles how to move. Space and time are not independent. And it's implementing this with one extra bit of information. So eventual contact with probabilities stems from the fact that the clock enables 3-way discrimination by a characteristic function, chi, that's either 0 or plus or minus 1. And thus the square of chi may be used as a probabilistic characteristic function, which is either a 0 or 1. So, okay, so what about the technical depth of this? What does this perspective allow you to do? Well, it allows you to derive the free particle Dirac and Schrodinger equations in 2 dimensions using only special relativity applied to 2-bit clocks. Okay, so you can go back through the arguments, and the thing is, you can do the derivation, and there's no formal analytic continuation, meaning there's no formal quantization. You don't have to do the sort of the usual cheat that one does when you try and produce quantum mechanics, which is to introduce either I or the Clifford algebra, an appropriate Clifford algebra, to bring in something that looks like the square root of -1. So the other interesting thing is that you can extend it to 4D, and it's really pretty straightforward. And it's consistent with the idea of 2-bit clocks, but in every time-like plane. The argument is nearly as immediate as in 2D, once the relation to space-time area is seen. The reason it hasn't been found until recently is because it's not an equivalent to the original conception of the path integral due to Feynman. So it in a sense flies in the face of thinking of quantum mechanics arriving from the analog of the world line by itself. So how far we got? Well, there's some inroads in including fields. That was done quite some years ago for the 2D case. The multi-particle case at this point is unexplored, but I'm hopeful in that it just seems that the generalization of multi-particle, I think, will go through. So where are we now? Well, the fragment of quantum mechanics covered is small, but it's central. Basically, free particles, relativistic and non-relativistic. So there's an elephant in the room in all this, and here we can see the elephant won't even fit into the frame. And that elephant is, well, this is so simple. Why on earth has it not been noticed? And this is really a question for sociology, but let me just take a stab at it. So Schrödinger's equation, like Schrödinger's stairs, is flat. Right? It does not contain the required information, that is boosts from Clifford algebra, to link wave function phase to relativistic time dilation. So combine that with the fact that the Dirac equation is almost universally produced at the level of partial differential equations, with a continuum already assumed. This obscures the counting arguments suggesting that wave functions enforce a relativistic equivalence principle. And the thing is, the completeness of a large fragment of quantum mechanics in Schrödinger's equation seems to suggest that we need not look to special relativity to find quantum weirdness. So this reinforces the misperception that quantum mechanics and special relativity are completely decoupled at the small v limit, which clearly from this they're not. Okay, so let's just do a quick comparison with the Broglie-Bohm picture. One characterization of the Bohm picture is particles and waves, as opposed to particles or waves. An unusual feature is that the particle, in this case, has to respond to a field that is generated by its own presence in the current environment. Well, the 2-bit clock has a similar feature, but the field is a manifestation of the relativity principle, the equivalence of inertial frames. And it's the whole idea that space-time tells particles how to move, which of course we accept in the classical context, but it really means that it's a statement about a whole ensemble of images. And when we extend that ensemble of images to a world signal, we see, well, okay, we have to adjust. So the 2-bit clock suggests that the quantum potential in the Bohm picture is a manifestation of space-time and the equivalence of inertial frames. Okay, so some quick conclusions. So here, let's just have a look at the advantages to the sort of the below-stairs route to the Dirac equation. When we look at this at the below-stairs perspective, what we're really saying is if you start with special relativity and you just say, push away the idea of the continuous waterline for a minute and just say, put a signal on it that is periodic, and then look at what happens to the theory when you do that, and you find that inner scale then distributes across the future light cone because of the equivalence principle, and that when you then follow that and ask, well, what happens if there are multiple paths between source and sink, then you actually have to inherit the machinery of the Dirac equation, in which just the wave function serves to eliminate inequivalent paths. So this below stairs picture has a distinct advantage over the above stairs perspective, because it starts in the classical world with special relativity intact, as opposed to putting in as an afterthought. We don't really want to if we're going to take a fundamental look at the whole thing, we don't really want to start in the approximation of the Newtonian theory, and then add relativity in as a correction. So in this below-stairs picture, quantization follows from special relativity by simply specifying a discrete periodic process at the Compton scale. And wave functions and the resulting superposition principle arise as a direct consequence of Lorentz covariance. So it's a fairly clean way of seeing what's going on. And we can see that the function of the wave function is known, right? It's simply a filter to preserve a discrete form of Lorentz covariance. And here, of course, we see the origin of the many paths with one particle is clear. It's the equivalence of inertial frames that's involved. Okay, those are the conclusions. And since this is sort of an online type thing, I want to end really with a comment and a little bit of outrageous advertising. So, I mean, I think there is a connection between many of the speakers in this series, in the sense that we all look at different perspectives, and that analogy of looking at things from different positions, I think, it's very strong. And I think particularly actually in terms of Lou and Peter's talks, there's an aspect of going right back to Plato's cave. So this was an allegory. So the way Plato looked at it, the whole process of learning and figuring out the world, he sort of thinks as human beings as like being slaves who are chained to a position where they only see shadows of images. So they just see projections of three-dimensional objects onto 2 dimensions, which of course is what happens with our retinas. And so our process of learning within Quicycle is a bit like this, that we all have these different perspectives, and it's only by adding the perspectives together that we begin to decipher the three-dimensional aspect of the world. And we, of course, we experience the world through projection. The projection is through our senses. So, yes, in a sense, we see only shadows. Now, thinking about Lou and Peter's work, Peter can give us back amazing amounts of physics and chemistry and even biology just by looking at the idea of the algebra, looking at Clifford algebra, and Lou can do the same thing, giving us a huge view of mathematics, just looking at the idea of commutators. And so I just want to leave you with a bit of an image that at some point it would be nice to fill in. Here's a matrix that just counts to 4, and my claim is all we have to do, in a sense, to see both the idea of Clifford algebras and commutators is to allow nature to count to 4. And what I mean by counting to 4 with this, well, think of sticking a column vector on the right-hand side of this and using the matrix as an operator. And we see, oh, yes, all this does is it just shifts. So we go from the first state to the second state. And if we keep applying this thing, we'll go down to state 4 and then back to state 0. Sorry, to state 1. So we look at that and we understand what that's doing. Now, we can do a transformation that says, instead of looking at these 4 states, we're going to look at the sum of states 1 and 3, the sum of states 2 and 4, the difference of 1 and 3, and the difference of 2 and 4. And when we do that, the operator looks like this. So we look at that, and so in the top left-hand corner, so this is block diagonal, and the top two states don't talk to the bottom two states. So this is a real projection, right? Where it's like old Plato's cave. If we're in one, we don't see the other. The top one is based on sigma x, and we saw in the original couple of talks that that's the basis of the thermodynamic clock. Now, the bottom right 2x2 is what Lou called his little Clifford algebra. This is it's a matrix with, of course, real numbers, but the eigenvalues are plus or minus I, and it's a four-state process. And when you look at that, you see that, oh well, from that you can generate a whole lot. And when you do that, well, you don't actually see the other eigenspace. These are two separate eigenspaces. They're orthogonal projections. And when you explore that idea, you can connect to both commutators and the Clifford algebras. So this is an advertisement for some time, hopefully this year. I'll give another talk, the last talk, which will be Clifford clocks and statistical mechanics. So that's the advertisement. All right, so thanks for listening. If there are any questions, that would be great.